Hello, everyone. We're back with another episode of Computer Vision Talks. And today we have with us Dian. She's a researcher from machine learning team at Toyota Research Institute and previously a researcher at Prof. Trevor Darrell's lab at University of California, Berkeley. She received her master's degree in robotics in 2019 at University of Pennsylvania, advised by Prof. Kostas. She's also working on 3D perception and domain adaptation. And today we're going to discuss her work, Contrastive Test Time Adaptation, which was accepted at CVPR 2022. And I'm super excited to host you. Over to you.
Right, thank you. And thanks for the invitation and also the introduction. I'm here very happy to introduce our work, AdaContrast, which is accepted at CVPR 2022. And yeah, so I'll first give you a brief outline of today's talk. So first, I will go into talk about challenges in real world data, and then what is test time adaptation actually. And then I will go over our actual proposed method, AdaContrast, and of course, and show you some good results and desirable properties of our method. And then I will go to the conclusions. So hopefully this will be a quite self-contained talk so that you can better understand what is the story, why we are doing this, and how we are achieving amazing results. And okay, so I will first talk about challenges in the real world data. So the problem we're dealing with is domain adaptation. Why? Because domain shifts happens in natural data. So let's say you have trained a classifier of planes. So you want to classify planes, and you have trained a classifier on real images. But in the world, there are not only real images. So let's say here you have also, let's say, simulated images. And if this isn't enough, you also have like various kinds of styles, let's say clip art and sketch. And if playing is not interesting enough, there are, of course, tons of other classes of objects. So essentially, in the real world, there are different styles, lighting conditions, and sim to real, etc. So basically, you can't expect your model is always seeing the same kind of data. And of course, the domain shifts will cause the model's performance to drop because, yeah, if your model is trained with real images, you can't really expect it to perform equally well on this, like, let's say, this doodle of planes and clock and axe and etc. So, yeah, to give you at a high level more a high level concept of what this really looks like. So here I'm drawing here like a feature space, and also here to introduce you to some terminology in domain adaptation. Here you can say there are two blobs, and I'm using solid line here for these two classes. So let's say we have two classes here, class A and B, or red and yellow, and this is what we call a source domain. And if your classifier is well trained, here you have received your well-trained decision boundaries. So that can well distinguish the two classes. But things aren't always perfect. So when domain shifts happen, your data distribution actually isn't as perfectly placed on both sides of the classifier. So here I'm using dashed line here to represent the target the target domain. So basically after the domain shift. Here, as you can see, this classifier, if you remain with the same classifier, it is not ideal anymore. So you can see here there might be some samples that will be misclassified based on this decision boundary. So let's say here you have two red triangles here that actually belongs to the other class. So, right, to give you like more concrete example in a source domain, let's say you are concerned with real images of plane, and after this domain shift, it might just be a doodle version of the plane. So that essentially tells you how domain adaptation is interesting and why the model performance is dropping. And to put it more concretely, domain shifts actually cause the model trained on source domain to drop performance on target domain. And here comes our central question to domain adaptation, which is how to achieve strong performance on target domain. So because this is what we are actually concerned about and we care about. So yeah, we still want to remain a strong performance. Okay, so actually in the last 10 years, I would say there is a very good understanding in what's called unsupervised domain adaptation. So, and here we have the source data in which we have the axes, which are images, and or in a broader level, it can be not just only images, it can be also text or other data formats, but conceptually you have your input data and also Ys, which are your labels. So this will be source image. And the reason this is called unsupervised domain adaptation is that for your target data, you don't have labels anymore. So you would only have access to the data you want to, let's say, inference on. So you have your axis from target from the target domain. And typically what unsupervised domain adaptation do is that the majority of the literature kind of revolve around the idea of feature space alignment. What that means is that conceptually it will try to perform domain confusion, basically to make the feature space, as I was drawing before, kind of domain agnostic. So so that it will no longer depend on the let's say domain of different images. But yeah, I am also putting a kind of a very representative work here, which is from 2015. You can feel free to check that out. But essentially, the unsupervised domain adaptation need to access both source and target data during the adaptation to arrive your final target model. Okay, so let's really zoom in to this sentence, which is need to access both source and target data during an adaptation. And what's the problem with it? Well, because the major problem is that source data is not always available, because nowadays, if we consider real world applications and under some real circumstances, you might have data privacy or transmission bandwidth, or even just data maintenance. So you can't always keep your source data from your users, let's say, to let's say everywhere. So your users don't even want you to grab their data to for various purposes. So these are very, let's say, realistic limitations to the unsupervised domain adaptation. So yeah, so here I will come to what is test time adaptation to address these kind of problems. So at its core, test time adaptation, or TTA. So these are kind of the acronyms for the algorithm. So it doesn't access source data. So at its core, it is source free. So you might also hear, you might also see some literature called source free adaptation. They're the same thing. So so yeah, this is the core of the algorithm. So it doesn't access source data. So you would have two stages actually. So first of all, you would have source training. So with your source data, you would first train a model. So which I'm using yellow here to represent that this model is trained on source. And actually on the TTA stage, you would actually take your trained model on source. You can say interchangeably, you copy or you init your model with the source weights, and you have your target data, you perform TTA to adapt, and the model will then become your adapted model on target. So yeah, at a very high level, this TTA regime essentially takes 4 steps, which is you take your source model and you take your target data and you adapt. And then after adaptation, you can just feel free to evaluate the model on your target data. So as you can see here, this is very convenient because you can just take your model, take your source model and store it anywhere. And when you want to adapt, you just initialize your model with the source copy. So which makes it essentially separate the adaptation from always accessing the source data. So this is very friendly to real world use cases under the aforementioned constraints. So basically like data privacy, transmission, so whatnot. And yeah, so TTA is very practical and appealing to real world applications. So that's why we are trying to investigate the problem. And it is not like a made up problem saying, hey, what if we take out the source data and see what the model can do? It actually arises from the real world needs. So it is both conceptually or scientifically and practically interesting to us. Okay, so as I was just mentioning, test time adaptation is not accessing source data, but this, which is good, but also it makes the problem challenging actually, because you have no source data and you have no target labels. How are you actually going to do the learning? How on earth can you do that? And since we are only given the source model, how do we actually to reuse the knowledge learned from source effectively? So we don't want to always start from scratch, and we still want to leverage the knowledge that we have from the source domain, because in domain adaptation, the assumption is that your source domain and target domain isn't like crazily different. So they might still have some correlation between them, although there are some shifts, but there might still be some knowledge that you can reuse. So here is our challenge also include that given only the source model without explicitly seeing the source data, how can we reuse the knowledge? And not only we want to conceptually achieve TTA, practically what properties are still very important to TTA to make it practically doable. So here are some questions we are thinking about when we are investigating the work. So okay, so here I'm coming to actually our proposed method, AdaContrast, which I'm going to go over, I guess, in a bit more detail. And at its core, is really it consists of two central ideas. The first of all is what is most apparent in the title, which is contrastive learning. Here we perform the joint self-supervised contrastive learning at test time. So this is a very high-level one-liner summary of the first idea. So in the intuition being that instance discrimination helps to learn a good target representation, and thus we can have better decision boundaries. So essentially we can have better performance on the target domain. So, and second idea is online pseudo labeling with refinement. So here is the second one-liner of the central ideas. So the intuition being that there are very useful priors in the pseudo labels, which can facilitate our knowledge reuse. So if you remember the questions we are considering just now, so these two are our solution to the mentioned question. So here is also, this is actually the figure 1 in our paper, which gives you a high-level comparison of what our model actually does. So yeah, so this might sound a lot mouthful. That's okay. I'm going to go over into a bit more detail, starting with the first idea, which is the contrastive learning part. And yeah, the intuition really comes a lot from the self-supervised representation learning, which was taking off for the past few years. Essentially, self-supervised contrastive learning is a very effective way in learning a good representation. So here I have put a very representative one called MoCo from Kai-Ming He. And the idea is that essentially, yeah, here you have your encoder, which is, let's say, ImageNet backbone, a backbone trained on ImageNet and initialized from scratch. What the ideal property you want your encoder to have is that, let's say you are given a picture of a dog, and you would want the 2 different versions of the same image, let's say a colored one and a color jittered one. And yeah, I'm just using the pictures conceptually. And you want the 2 versions of the same image to have the features which are very close to each other. So as you can see, the gray dots here. And at the same time, you would also want the model to produce a feature, let's say, of a cat, or essentially a different image to have a feature that's far away from each other. So this is the high-level idea of contrastive learning. You want to pull some example closer in the feature space, whereas push apart some examples in the feature space. And here, some examples here are same image, but different versions versus different images. That's what we call instance discrimination. And if you are kind of familiar with self-supervised contrastive learning, or in a broader general regime representation learning, what people usually do is that they will first use this algorithm for pre-training on ImageNet with a from scratch initialized encoder. And after the pre-training, they will then fine-tune the encoder along with a classifier to produce their classification of a dog, let's say. So because here, the downstream task for them is usually the classification, but on a high level, this is a very effective pre-training paradigm. And yeah, and MoCo is one way that's proven to be very effective to realize the contrastive learning without a huge batch size. And here, what we're trying to do with test time adaptation is that we want to use this idea for also learning a good representation on target. So this is called joint self-supervised contrastive learning. By joint, I will talk a bit more later why this is called joint. But the essential idea is that we also want to apply instance discrimination on target data instead of your usual familiar ImageNet, but on target data instead, to achieve the to get a good adapted representation for the model. So here we still have your encoder, but here it is not initialized from scratch. It is instead initialized from your source model. So this is the number one biggest distinction from the representation learning as I was mentioning, because by initializing your model with source weights is a very effective way of using reusing your knowledge from source apparently. So here, let's say in the target domain, I have 2 versions of the same plane. Here you might see they are really different because in practice, you have to apply a very strong data augmentation to the same image to make the method really work. So here, let's say I have two versions of the airplane, and in the target domain, I also have a unrelevant image, let's say an apple. Same, I want to do the same thing on them. So I want to pull the representation of the two planes together, whereas I want to push the apples of the representation of the apple away from the plane. So yeah, so this is the part from the main figure of the joint self-supervised contrastive learning. So why is it called joint? Is it because the self-supervised objective is actually optimized together with several other terms. So you are not adopting a two-stage pre-training and fine-tuning regime. You are actually using this objective during the adaptation jointly with other terms. So here you initialize your target model with source models. I have put them in bold here as a focus. So you initialize your source model first, and then you perform instance discrimination with the momentum model and memory queue. And the momentum and memory queue actually come from the MoCo idea, which is a very good way and stable for the contrastive learning without needing a huge batch size. And also what's on top of that is that we also exclude the same class negatives indicated by pseudo labels. So the idea is that let's say we want to push two instances away from each other, but what if we know the two instances are both, let's say, plain? So intuitively, you also don't want to push the same class from away from each other. But you might say, okay, I'm on target domain. How do I know they are planes? Actually, this is indicated by pseudo labels, and yeah, the pseudo labels can give us a very good idea of how the class of the samples are. So speaking of pseudo labels, let me then go to the second point, because some of you might not be familiar with pseudo labeling, and which is also the second pieces to our algorithm. Let me actually come to the pseudo labeling, which will hopefully resolve some of your confusion. So pseudo labeling on target, why we do that is because pseudo labels actually carry knowledge learned from source data. Because as I was saying, the source domain and target domain might not be like super far away from each other. They might still share some structure. So your pseudo labels might still carry useful knowledge from the source data. So some of you guys, you are hearing me talking pseudo labels all the way, but what are pseudo labels really? So let's say you have an image of a plane here. You pass it through your encoder to get the feature, which will then be classified into, let's say, logits here. So even though you don't really know the underlying ground truth label for this image, the prediction from the model might still make sense to some extent. So it is not like entirely garbage, but there is a high chance that the prediction from the model still makes some sense to you. So essentially, pseudo labeling is really simple, which is you take your prediction of the model and you simply take an argmax, let's say, if you want to use a hard pseudo label, or if you just want to use a soft version of pseudo labels, you can just take the confidence scores, let's say. So basically, pseudo labels are really just taking the output of the model and treat them as if they are ground truth labels to retrain the model with. So these sounds kind of a bit magical, but it is it is a very effective way of reusing knowledge of your model, and in a sort of self-distillation sense. So yeah, I also put a simple equation of cross entropy. Hopefully you can recognize this is cross entropy. And the difference you can notice here is that I have put a hat on the y here. The hat being that this y is not from ground truth. It is from our estimation or our prediction. So this is actually saying that this y is pseudo label. And yeah, and if you compare some different paradigms and how this pseudo labeling is compared in our method. So let's say you have in A, we have source only, which is that you don't do any adaptation and you just start from your sample and just get your pseudo labels directly. And in B, in pseudo labels, what we put a circle here, which means that we actually use the pseudo label to do some retraining or pseudo label fine tuning or self-training. So these terms are kind of interchangeable in the literature if you ever run into them. And also there is a short paper which I also put the title down here. You can check that out, which is a very representative work in test time adaptation or source-free adaptation. Here they actually, so they took the pseudo label and with some offline refinement. So let's say after every epoch, they do some refinement to their pseudo labels, basically to get a better quality set of pseudo labels to retrain their model. And here, what we are doing here instead is that we do a way of online refinement, in the sense that we take the pseudo labels at a per step basis and we refine them at a per step basis. And at the same time, we have the contrastive learning working on the samples and to get a better representation. So that's the comparison of our paradigm with all the other, let's say, terminologies you might run into. And let's again come to our figurative imagination feature space to give you a better idea. So what we call in online pseudo labeling with refinement is that the target space, the target feature space might still be structured to help recover the correct label. So let's say if we are looking at this black dot here, so this might be actually belong, this might belong actually to the yellow class, but given this classifier, which is not adapted yet, it might actually get a wrong assigned class, which is the class will say this is a triangle for the pseudo label. But actually, if we look around in the feature space, we might get some useful knowledge from the neighbors. So let's say we consider, let's say, top K neighbors. Here, there are the triangles, there are the yellow dots. What we do here is that you can do a very simple and intuitive thing. So you can do just a majority voting or soft voting, what have you. But here we show that by simply average the samples prediction score, you can get a much refined pseudo label for this originally misclassified sample. So after doing this, by taking the average, and then you take the argmax here to get your y hat, there is a high chance you can recover the correct underlying class as your pseudo labels. Okay, so on the high level, this is the main figure from the paper again. So this is the part that is performing the online pseudo labeling with refinement. So essentially, it aggregates knowledge of the neighbors in the target space by averaging the probabilities, which are really simple. There is no tricks or other hyperparameters behind that. It is just averaging and taking the argmax. And the conceptual feature space is maintained as a memory queue, which is lightweight and very practical as an your continuous estimation of the feature space. And what's most important is that we produce and refine the pseudo labels at each iteration. So let's say your model is already adapted to some good extent. You don't always want your model to stick with the old pseudo labels. So essentially you want your progress in the adaptation to be reflected in your pseudo labels at a very per step basis. So you can always incorporate the best knowledge or the freshest knowledge for the model. So yeah, so it is done at each iteration, which is also very helpful for the performance. And lastly, there are some additional regularizations to help the model more robust and have better performance. The first one is weak strong consistency. What I mean by that is that you can see here I have 3 versions of the same image, and the contrastive learning is performed on the 2 strong augmented version, as you might be familiar with in the literature. And here for the pseudo labels, I'm actually using a weakly augmented version here to get the feature space and to find the neighbors and eventually get the pseudo labels. So here we found that using a weak version can actually give you a more stable target feature space to avoid more to avoid the strong fluctuation of feature points. So that is kind of intuitive, because in the strong version your images might be drastically different, so the feature might jump a lot in the feature space. But instead, using a weak version, you can get a smoother change of your feature space, and thus you have better or more stable pseudo labels. And the second of that is diversity regularization, which is essentially this div term here. What this does is on a high level, basically prevents the model from over trusting the pseudo labels, because even though the pseudo labels are great, they might not be perfect, because otherwise we have already reached an ideal world. So there are still some noise in the pseudo labels. So we want the model to not over trust all the pseudo labels. So that will give us more robustness in the adaptation. Okay, so here are basically the overall framework of AdaContrast. So the main figure might seem quite a mouthful to you at first glance, but hopefully after the decomposition of what I just said, I can help you better understand what we are doing. So essentially we have 3 loss terms here. The first one is pseudo labeling, which is, yeah, very simple, the pseudo labeling with cross entropy. And the second one is the joint self-supervised learning which is instance discrimination on the target data. And the third term is the extra regularization to help the model be more robust and smoother. And yeah, so that's what we meant by joint optimization of the self-supervised learning. So yeah, hopefully this is a good illustration of what we are doing. And of course, let's come to some results. And I'm actually more excited to talk about the properties here. But before we jump into results head first, let me tell you what we are doing for the evaluation. So for the benchmarks, what we're doing is really simple. We're just evaluating the class accuracies on the target domains under multiple domain shifts. So here we are considering 2 major large-scale domain adaptation benchmarks. The first one is VSTAC, which contains 12 categories, 2 domains, and yeah, about 300,000 images. So here we have the real domain and the simulation domain. So people do evaluate on sim to real or real to sim. So there are two domain shifts you can consider. And here another very large scale benchmark is called Domainnet. It actually consists quite some categories. There are over 300 categories and 6 domains. And as you can see, you have your normal real images, and you have your sketch images, and you have this really funny doodle-like images. This is collected with Google Doodling, I think. And this one called Quick Draw is actually one of the most challenging domain. As you can see, these are really just a few lines, and some of them might not even make sense to human, but yeah, as a human, you might still pick up the structure, but you can say, you can really tell that they are really challenging. And yeah, there are 6 domains and 0.6 million images, which is a really large scale. Okay, so apparently we achieve a state-of-the-art performance on these 2 benchmarks. I'm highlighting our numbers here. And if you look at the last few rows, and oh, by the way, this on-target work is also a concurrent work from our lab back then. And you can think of it as a wrapper around any adaptation method, and to do an extra step of that adaptation to give you a further further few points of boost. So here we apply AdaContrast, which already has the state-of-the-art performance if you don't consider this magical wrapper. But if you apply this on-target wrapper on top of it, you can see that it is even going further. And if you consider this shot, which is one of the previous state-of-the-art, we also apply this wrapper on shot. But as you can see, even before and both before and after applying this on-target paper on top of the method, we're always state-of-the-art. And yeah, on Domainnet, we are also outperforming shot and other baselines, and even with a strong performance on the online setting, which I'm gonna talk about a bit later. So yeah, so that's for some boring numbers as state-of-the-art performance. But what I'm actually quite excited is that we also achieved some desirable TTA or test random adaptation properties for AdaContrast. So the first of all is that AdaContrast is well calibrated on target data. So by well calibrated, what I mean is that so conceptually, calibration, you can think of it as a property of a model that says if your model produce higher confidence of a sample, if it has a higher confidence to be classified, let's say as class A, then it is its accuracy is going to be like correspondingly high on the data. So if your model is not producing a very high confidence, or let's say a low confidence score on a sample, so the chance the model is doing right is also low. So that is a very good, I would say, metric or a good indicator of how your model is confident and is confident on the data it is performing on. So you don't want your model to be overconfident, saying, hey, I know this class is 100% class B, the other image is 100% class C, but actually it is not doing right. So we want this type of chance or accuracy in the performance to be also reflected in the model's predicted confidence score. So that's what we mean by by good calibration. So this is really good for deployment safety. So you don't want to adapt your model and let it confidently say, hey, I know this and this and this very confidently, but we still want our model on the target domain to give you a good indicator of knowing when it is confident and when it is not super confident. So you might want to put a thresh or regularize your output. So here, I was talking all the way, but figuratively or on this figure, what it is showing here is that ideally you want this bar to be closer to the diagonal. So so on the x-axis, you are taking, let's say, 10 bins of your confidence score and count the numbers of the samples you are actually predicting as, let's say, 90%, 90% confidence score or 60% confidence score. You want to put them into bins and count them in total. And ideally, you would want this figure to have a diagonal shape. That means your model is well calibrated. So here I'm showing one of the representative work called SHOT. And you can see that SHOT here is not very well calibrated. So there is a huge gap here. The reason is that SHOT directly optimize the entropy on the target data to achieve good performance. So there is a bunch of literature that has found if I directly optimize the entropy on target data, it can be very effective to achieve good performance. So you can say SHOT and TENT, if you have heard of TENT, and some other works alike, which optimize the entropy, which is good, can give you good performance. But if you consider calibration, since they are directly working on the confidence scores, it is going to disrupt the entire calibration. So that's the number one property we want to have here. And second and third, I'm kind of putting them together, is that AdaContrast is memory efficient. So if you look at on the left, as you might remember, we have a memory queue similar to MoCo, but we have shown that we can just maintain a mid-size memory queue to achieve reasonable performance. So this is evaluated on Vista C. And as you can see, with a mid-size memory queue, we can already achieve quite consistently good performance without going to a very extreme. That doesn't really give you too much. So we can be good with a mid-sized memory queue, which is efficient. And also, we are robust to hyperparameters. This is another I would say a very good property in all test time adaptation methods, because this is a property that is under investigated, because previously there are a lot of methods in test time adaptation which are super cool, but this hyperparameter robustness is kind of under investigated. So people report amazing numbers, but they might not tell you how they have reached the hyperparameters. Let's say the learning rate and the weights of the losses, because ideally you don't have access to your target labels, which means ideally you can't really do hyperparameter optimization as you would on the supervised data sets on the validation held out sets. So here, since your target data doesn't actually have any labels, you can't really optimize the hyperparameters. So here, what we have shown here is that, let's say, we have shown here that our model is Okay, so here we have shown here that our model is very robust to hyperparameters. So as you can see here, we have tested across the number of neighbors in our pseudo label refinement. We can achieve consistently good performance over a wide range of choices. And we have also shown that under a wide range of learning rate, we can achieve consistently good numbers. Whereas on some unfortunate learning rate, some other methods might have deteriorated performance. And here is also an ablation showing which part is making our model very robust. As you can see, this joint contrastive learning here is really bringing the robustness to our model to a large extent. And yeah, and last but not least is that AdaContrast is also very strong in online TTA setting. By online, I mean that the test or target samples are arriving in a stream-like fashion. So you saw an example and you never saw it again. And this is actually a very challenging setting because you only get to see the samples once for the model, whereas in the standard setting, so for the main results, we apply the standard setting, which we can still optimize, let's say 10 epochs pretty fast, but we still see the samples for 10 times. But here, if we are going online, we only get to see the samples for just one time in a stream fashion. So here, as you can see, our online test time performance is also very strong. And you can see here, it even exceeds some of the previous unsupervised domain adaptation methods. So yeah, it is strong in online setting. Okay, yeah, so after talking about the results and desirable properties, I want to kind of conclude the method to give it a summary. So too long didn't read. I have 5 bullet points here for you. So basically, AdaContrast performs test time adaptation, which doesn't access source data. And we propose a novel way to leverage self-supervised contrastive learning and online pseudo labeling for the adaptation, which are the 2 central pieces of our algorithm. And thirdly is that AdaContrast achieves state-of-the-art performance on a wide range of domain shifts. With AdaContrast is also memory efficient, robust to hyperparameters, and has great model calibration, which are all desirable properties for test time adaptation. And lastly, it is very strong in online test time adaptation setting. And right, I also kind of want to talk about some future direction because I got asked by some people sometimes a lot about the test time adaptations relation with continual learning. So I think some people, when they are coming from continual learning regime, they might want to know the difference, but and they want to know when to use test time adaptation and when to use continual learning. So I think if people have similar concerns, I think there are 2 questions you really want to ask yourself. The first one is that, do you have labels on target domains, or in continual learning, you would mean future domains? So sometimes in continual learning, when the domains are arriving on a, let's say, per day basis, sometimes they still have labels, which makes the problem kind of different than unsupervised adaptation, because one has label and the other doesn't. And the second question is that, do you still care about the performance of your source domains? And in the continual learning setting, you might know this as past domains or your past classes of data. So if you still care about the performance on the source domains, you might want to combine continual learning with test time adaptation. But if you care more about the target data, or let's say in the future domains, maybe you can consider more about on the test time adaptation. So I think that kind of hopefully clarifies some of the questions. And as for second direction, is that I'm talking about all classification here. which seem like a toy example of all the underlying algorithm. But actually, test-time adaptation is going to be applied in some real-world cases. So, for example, I'm also working on 3D perception, including detection and depth estimation. What I can tell is that test-time refinement, which is essentially a form of test-time adaptation, is just because people from two fields are not talking to each other, so the terms are different. But essentially, a form of test-time adaptation is already used in depth estimation via self-supervised fine-tuning. So on a high level, it shares some similar idea, which is that you have some signal derived in a self-supervised way, and you use this self-supervised signal to fine-tune your model or let your model adapt to the data that you are mostly care about. So that is also one example of applying this classification idea to some actual real-world applications. Yeah, okay. I think that's my overall presentation for the work, for our work for the CVPR 2022. And we have code, and also feel free to check out the project page and the code. And really, I want to thank you to invite me here to talk in detail of this work. And thanks.
I'm so glad I invited you, because you've almost covered a lot of doubts that I had in mind, but now I have no doubts. So
cool.
Okay, so I'll start with the one in chat first, because I think that was for first slide. Kunal was asking, how is this kind of data created? When you were talking about, I think, the aeroplane data, the data with corruptions, I think.
Okay, so maybe I can.
And also, if anyone wants to unmute themselves and talk, just do drop in the chat, and I'll let you unmute yourself. Actually, yeah.
Okay. Let me go to the very beginning. Do you mean this data?
Kunal, do you want to unmute yourself and talk?
Yeah, hi. Yeah, thank you for the good presentation. Can you please explain how this kind of data is created?
So this data is created by some other work. So yeah, actually, let me go to the benchmark slide. Okay, so the first one is called Vista C. So basically, and the second one is Domainnet. And basically what they did is they collect, let's say, a few hundred categories, and they want to collect different domains. So that's essentially what they create the data set. So they have images from different domains. And so you can say there are different versions of a plane, and they have ground truth labels for each and every sample in every domain. But when we evaluate and when we do the adaptation and evaluate on the target domain, we just don't use the ground truth on the target. We only use the labels for evaluation purpose, and we just don't use the labels for adaptation. So that's how we use the data.
So the doubt is that there is no sense of orientation. Just like you can see the plane can be oriented in any direction, but you still want them to match in terms of features. They can be in any other domain, and you just want the features to be matched. That is the whole idea.
Right. So here we are considering just 2D images, so we don't really consider facing left or facing right. To us, it's only 2D images. So for classification task,
where we consider self-supervised training by rotation features, just by rotating the original image, and they try to learn the features there.
Right. So if you're talking about the test time training paper, which is also from Trevor's lab, I think in that paper, one major distinction is that you might know they apply the rotation prediction as a self-supervised signal, but the major distinction is that they also apply the task during source training. So that is one. Let me go to. Sorry. So so here, ideally for test time adaptation, you are only given the source model. However, this source model is trained. So for test time training, what they're also touching is the source training. So they require the rotation prediction to be also applied during the source training, which we think might not be ideal because that is an extra constraint you are putting on the source training. Here, we are only touching this adaptation phase, which doesn't really require your source model is trained in any particular way. So you just take any source model weights and you can just start your adaptation. So I think that's one major difference.
Okay.
Awesome.
Yeah, hi Dan. Can I go next?
Yes, sure, Vikas. Go next.
Yeah, okay. Yeah, so I mean, I had two questions. So first is that, since you're in your online setup, you cannot access the more number of target domains to find the nearest neighbors. So how are you defining your pseudo label in that case? Or is that lost on the drop in that case?
I'm sorry, I didn't catch that clearly.
So he's asking that in the, yeah. Do you want to reframe it, Vikas?
Yeah, sure. Yeah. So in your test time adaptation, we cannot have a lot of target samples to find the nearest neighbor and define your pseudo levels. So how do you tackle this problem in your online pseudo level defining?
Okay, so I guess I can go into a little bit more detail in terms of implementation. So so here I'm showing a conceptual feature space here, but actually it is implemented by a slowly updating queue. So it's similar to a memory queue, and which is slowly updated by the features from the weak augmented images. So it is not like a perfect, a real-time feature space, you might say, but it is a very effective way of our estimation of the current feature space. So the model is evolving. So the feature space is evolving accordingly. But here we are using also a mid-sized memory queue to represent this feature space here. So whenever we want to find the nearest neighbor, we just take the samples feature, let's say this W here, and we just find the nearest neighbors according to cosine distance. And let's say you have 5 nearest neighbors, and you just do the voting, soft voting, which is in practice just an average of their confidence score. So
you are storing those features, right, in the queue?
I'm sorry?
So you are storing those features in the queue, right?
Yes, yes, they are stored in a queue.
That's the part similar to MoCo.
Yeah, so my second question is that you said that, in your paper, right, the model calibration is really nice. So is it a byproduct of your work, or you did something to achieve this particular object?
I'm sorry, I didn't quite catch that.
So I mean, it came naturally, or you had to apply some additional regularization, keeping this problem prior in mind that I want to achieve this objective to have a very good model calibration.
I can reframe it.
Right,
it.
yeah, sorry, the volume is not
Yeah, the volume is a bit low. So sorry, Vikas, I'll just reframe it for you. So he was asking that when you talk about the model calibration accept of your work, so is it just a byproduct of your research findings, or did you put some extra effort or some extra fine tuning to achieve it?
Oh, okay, I think that's a very good question. So here, I think it's not that we deliberately want to achieve good calibration, but in our mind, we still want to avoid using entropy minimization, because that's what we know from our experiment. And also conceptually, if you directly optimize the confidence score on target, that will destroy your confidence, sort of. So because you are only caring about the right the right results, but you are entirely disrupting the confidence space. So we are not like super centered on finding a perfectly calibrated model, but we do when we are when we are deriving this algorithm, we do want to sort of stay away from using entropy minimization. So that naturally leads to better calibration.
Okay, so this gives me two questions. One is that when you talk about how tent fails so bad that like you're able to improve over 10% on tent on Domainnet. So is this reason of entropy minimization behind tent's failing?
I think tent is also kind of, sometimes it needs some tuning to get good performance. So sometimes tent can do really well. And there are some cases, if you don't choose the right hyperparameters, tent might not be ideal on your data. So I think that is why tent is not, let's say, super performant on this Domainnet, because back at that time when tent was published, people don't usually evaluate Domainnet because Domainnet is really challenging and large scale. But here we actually are, I think, the first to evaluate on this really large scale comprehensively for the TTA task. And I think tent is still very performant, but it needs some tuning to some extent. Yeah.
Okay, before
we are, yeah, sorry.
No, please go ahead.
All right, I just mean that here we are robust to the hyperparameters, so which gives us good performance consistently. And by the way, we also just didn't tune the weighting of the different loss terms. We just go with 111, and that's all we did. We didn't do any extra fine tuning.
And in your implementation on GitHub, can we reproduce the results you got on tent as well?
I don't have tent included in the GitHub repo, but I think I just took the open source tent as well. I'm not like using any internal code. I just grab the public tent, and I think
without any changes.
Yeah, right, without any changes, you can also, yes.
Cool. Also, there's a comment from Bala. He says that diversity regularization term is used and that provides the expected calibration. He thinks this might be the reason.
I'm sorry, could you say that again?
He says that maybe the diversity regularization term that is being used provides the expected calibration.
Oh, I see. I think that helps to some extent, but you might also, if you check tent paper and some later version of tent, which I think is the on target paper, they also use this diversification term. So in tent, they also use that as some boost for the performance, and also prevent the model from overtrusting the model, from overtrusting the pseudo labels. But still, I think the major source that disrupts the calibration is the entropy minimization.
I see. Okay, one more question is that because we're talking so much about calibration being a desired property of test time adaptation, why not simply use a well-calibrated model instead of going through all of the test time adaptation techniques?
Right, yeah. I think that goes all the way to the beginning of why are we even doing test time adaptation? Because if you have labels on target, then of course, go ahead. You can just train a very good model on your target data. But here, why we are doing test time adaptation is that, first of all, we don't have target labels, because underlying it is still unsupervised domain adaptation problem. So with even more challenging setting.
I see. I have the last question, but if anyone wants to ask anything, please put it in the chat box right now, because I'm going to conclude with my question. So I was reading a recent paper from ICML 2022, which was comparing TTT, the method you mentioned earlier, and MeMo. And they said that during the test time adaptation, we need to compute one round or even multiple rounds of backward computation for each sample, which is not just time consuming, but also not very favorable for latency sensitive applications. So when we talk about the backward computation, how would you rate or judge AdaContrast over there? Does it even matter? Like, did you even consider the backward computation while like while you were doing this work?
I see. I think doing that might give you some further boost in performance, which kind of makes sense. But as you were just mentioning, it is time consuming, and sometimes you can't on the hardware level, you simply cannot just make multiple backward rounds of the data. And I think AdaContrast is kind of simple in conceptually simple, which is that you simply take your target data and you adapt multiple epochs, let's say 10, which is a reasonable number, 10 epochs of adaptation without any labels. And it can be really strong. And if you are concerned with online adapting, as I was just mentioning, AdaContrast is also super performant with online setting, which means you only have your data coming in once, and you adapt your model, and the data is gone, and you never see it again. I think, yeah. I think that is a good aspect of that as well.
Okay, although this next question might not be even fair, because you already clarified that test time adaptation is different from content learning in certain aspects. But just say we have the in-distribution data given back to AdaContrast, like the source data on which it was trained on. How do you think it would still perform on it? Do you think there would be a performance degradation, or how far?
Do you mean you are given source data again?
Yes.
I think if you are given source data, then feel free to use one of the unsupervised domain adaptation. Here. Yeah, here. So unsupervised or UDA, I think this regime is very mature, and there are a lot of competitive methods. And essentially, the distinction from TTA and UDA here is that we don't assume source data. But if you do, then go ahead and use them. And as you were just mentioning, if you even have target labels, then go ahead and train them in your usual supervised way. That's even better. But here we are investigating under a very constrained scenario, how we can get good performance, which is TTA.
Interesting. Awesome. So I think that was all from us. And thank you so much for giving us your time, and that too on such a short notice. Like this, just 1 week, and you had the talk ready. And so
ask a little more. Can I ask a little more? Sorry, I didn't ask.
yeah,
Okay.
sure.
Just one question about privacy. Like you have mentioned that test time domain adaptation has in privacy, but how is that? Because you're still using that data at the test time, right? How? But you labels for that. How is it privacy preserving?
So here, by privacy, we meant the privacy in source data. So let's say the customer, you have some data and you train the model on the data, and usually the company can ship the model, but instead of the data. So because the customer, let's say you use Facebook or YouTube, you don't always want your photo to be shared across different companies, but if a model is trained, usually the company is feel free to distribute the models to different clients for the downstream TTA fine tuning or adaptation.
I see.
Yeah.
Okay.
Okay, so a wide range of questions from different domains, but
right, I think that's good. Yeah.
I'm thankful to you for answering all of them so patiently.
Right. No problem. Because I think test time adaptation is really coming out in recent years. So it is not a super mature or very well understand problem. So I hope this will help clarify some distinction, differences, and confusion. So I hope this will also help the community in advancing in the regime.
For sure. Thank you so much. And we look forward to more awesome work from you.
Right. Thanks. And I really thank you for inviting me here. And also, let me also give you the QR code. Feel free to check our code. And reach out to me for any questions.
Thank
Right,
you.
thanks.
Thank you, everyone. Goodbye. Have a nice weekend.
Bye.
Thank you.